In this video, we're going to talk about how to graph rational functions. And I'm going to give you a process, if you're new to this, how to work through these problems. We're going to go through 5 examples. We're going to talk about how to find the asymptotes, how to find the intercepts, how to find out if there's any holes in the graph or slant asymptotes, how to plot some additional points, how to do some sign analysis to get a pretty good sketch of these rational functions. We're going to go through 5 different examples. Let's dive in. The first example, f of x equals x minus 2 over x squared minus x minus 6. If you want to practice, go ahead and pause the video and try this on your own. But the first thing that I like to do is factor the rational function as much as I can. So the numerator, we can't really factor that. That's just going to stay as x minus 2. The denominator, though, we can factor this trinomial. What two numbers multiply to negative 6 but add to negative 1? Well, that's going to be negative 3 and positive 2. Now, the reason I factor this is because if a factor in the numerator cancels with a factor in the denominator, what's going to happen is we're going to have like a hole, like a removable discontinuity or a missing point in our graph. In this case, there's nothing that cancels numerator and denominator, and no factors. So that tells us that there's actually going to be no holes in our graph. So I'll just write none for holes. Okay, now, when you're talking about rational functions, just so you know, rational just means a ratio. So it's like a fraction, okay? So you've got like a polynomial divided by a polynomial. Now, when we talk about the vertical asymptotes, well, when you look at a fraction, you can never divide by 0, right? Because that's undefined. So we can see here that if x is equal to 3, 3 minus 3 is 0. And so that would make this undefined. Same thing here. If x was negative 2, negative 2 plus 2 is 0. So what happens here is we're going to have vertical asymptotes at x equals 3 and x equals negative 2. Now, what I like to do is, as I figure things out over here, I like to kind of graph it as I go. So x equals 3 is a vertical line right here. And x equals negative 2 is also a vertical line going through negative 2. Okay, so now let's talk about the horizontal asymptotes or the slant asymptotes. So when you're analyzing whether it has a horizontal or a slant, you look at the highest powered term in the numerator and the highest powered term in the denominator. Now, if the denominator's degree is higher than the numerator's degree, then the horizontal asymptote is going to be the line y equals 0. Okay, and the way to understand that is, imagine as x gets larger and larger. Like if I put in 100 for x, 100 squared is 10,000, right? And this is 100. 100 divided by 10,000, that's going to be a very small number. It's getting closer and closer to 0. So what that means is as x gets larger and larger as you go to the right, or as x goes to, let's say, negative infinity, you go to the left, this whole fraction is going to get smaller and smaller. It's going to go to 0. And so that's why we have our horizontal asymptote of y equals 0. Now you might be saying, Mario, what about these other terms here? Well, you can see this x squared is growing faster than this x. So as x gets bigger and bigger, this term is going to basically outpace these guys here. Same thing in the numerator. This is going to be growing much faster than minus 2. So as x gets really big, this kind of acts more like x over x squared. And that's how we're getting that horizontal asymptote here, which in this case is right at the x-axis. I kind of like to put the asymptote kind of like on a little bit of a diagonal like that, just so that I can see it. It doesn't blend in with the x-axis. Okay, now for the y-intercept. So y-intercept means where does it cross the y-axis? Well, that's going to occur when x is equal to 0. Okay, because when x is 0, you're not going left or right. You're just along this vertical y-axis here. So if I put 0 in for x, that's going to cancel out this term, and this term. So anything that has an x in it, those guys are going to cancel out. And you can see we have negative 2 divided by negative 6, which is 1/3. So there is our y-intercept, 0, 1/3, which is right about here. Now for our x-intercept, we do the opposite. We set y equal to 0. And in order for f of x or y to be equal to 0, the only way this is going to be 0 is if the numerator is 0, right? Because if you have a fraction, the numerator is 0 and the denominator is not 0, that whole fraction is going to be equal to 0. So a shortcut is just to set the numerator's factors to 0, and that's going to give you 2. So in this case, we have an x-intercept of 2 right here. Now, for some students, that might seem a little bit confusing. So what you might want to do is you might want to do this. You might want to say, well, Mario said set y to 0, so that's going to be f of x is equal to 0. 0 is like 0 over 1, right? Because anything divided by 1 is itself. That's still going to be 0. And then over here we have x minus 2 over x minus 3 times x plus 2. Now you know the cross product where you multiply on the diagonals. So 0 times this quantity gives us 0, and x minus 2 times 1 is itself. And then if we add 2 to both sides, you can see we're getting x equals 2. That's another way to do it. It's just to do that cross product. Okay, now we've got some pretty good framework here. We have our vertical asymptotes, we have our horizontal asymptote, we have our intercepts. The thing to focus on now are some additional points to help us to get a good graph here. Now what's interesting is you can cross a horizontal asymptote, but you cannot cross a vertical asymptote. And the reason is because if x was negative 2, we talked about this earlier, you'd be dividing by 0, it's undefined. Same thing over here with 3. So what happens is when you approach a vertical asymptote, it's like a brick wall. You either have to turn up towards positive infinity or down towards negative infinity. You can't go through that vertical asymptote. So what I like to do is I like to pick some points on either side of the vertical asymptotes. And what we're going to do is what's called sign analysis. So for example, if I pick like a negative 2.5, okay, let's just put this in our table here, negative 2.5. I'm going to just put it in this factored form right here. So negative 2.5 minus 2 is negative 4.5, but I'm just going to write it as a negative. Okay, I'm not going to focus on the number. I'm just going to focus on whether it's negative or positive. Negative 2.5 minus 3 is negative 5.5. That's negative. Negative 2.5 times, or plus 2 is a negative 0.5. That's negative. And notice what we have here. A negative times a negative is a positive. A negative divided by a positive is a negative. So what that tells me is that negative 2.5, this graph is going down towards negative infinity. Now, if you want to get an actual number, go ahead. You can certainly do that. But the main thing is it's going down as you get closer to this vertical asymptote. And when you go this direction, you're approaching this horizontal asymptote at y equals 0. So you can see here we're getting this branch of the graph. Now let's pick a point on this side of the vertical asymptote. Maybe let's do negative 1.5. So if we plug in negative 1.5, we get a negative 3.5, a negative 4.5, and a positive 0.5. So now look what we have. We have a negative times a positive, which is a negative in the denominator. Negative divided by a negative is a positive. That tells us when we're approaching this asymptote from this side, it's going up towards positive infinity. So here you can see the graph kind of looking like this, right? Now let's pick a point on this side of the vertical asymptote, maybe 2.5. So if we plug in 2.5, let's see, we get a 0.5, which is positive. 2.5 minus 3 is going to be a negative. 2.5 plus 2 is a positive. And you can see a negative times a positive is a negative. And a positive divided by a negative is a negative. And that tells us this is going down towards negative infinity. So you can see this branch of the graph looks something like that. And then over here, let's pick maybe 4 would be an easy one. So if we plug in 4, what do we get? We get positive in the numerator. 4 minus 3 is positive. 4 plus 2 is positive. So we're getting a positive divided by a positive, which is a positive. That tells us this is going up towards positive infinity. And then it's approaching the horizontal asymptote as x gets larger and larger. So you can see we have a pretty good sketch of our graph. The only other question your teacher might ask is like, what's the domain of this rational function? And again, we said that the denominator can't be 0, okay? So it can't be 3 or negative 2. So you could say all real numbers, x cannot be, will we say negative 2 or 3. That's one way to do it. Or if you're doing interval notation, you could say it goes from negative infinity up to negative 2, not including negative 2. Then it goes from negative 2 to positive 3, not including, so that's why we're using the parentheses. And then from positive 3 on to positive infinity, and that would be your domain. So let's take a look at another example. Okay, now for example number 2, we've got x squared minus 9 over x squared minus x minus 12. So what's the first thing we want to do? We want to factor it as much as we can. So the numerator is the difference of two squares. So we factor that as x minus 3, x plus 3, a sum and difference pattern. The denominator, it's a trinomial with a leading coefficient of 1. So we say what two numbers multiply to negative 12, but add to negative 1. That's going to be, let's see, minus 4 and plus 3. And the reason we do that is because we're looking to see if there's any factors in the numerator that cancel with factors in the denominator. And in this case, you can see that x plus 3's are going to cancel. And what that tells us is that we're going to have a hole in our graph. If you set x plus 3 equal to 0 and solve, we get the x coordinate of the hole, which is negative 3. To find the y coordinate of the hole, we take the negative 3 and we put it back in to what's left here. So we get a negative 6 over a negative 7, which is 6/7. So let's go ahead and plot that on our graph. So negative 3, 6/7 is almost up to 1, but not quite. So we'll just right about here, that's our hole. Now, as far as the graph is concerned, it's basically like graphing y equals x minus 3 over x minus 4 because these factors cancel. The only added feature is that there's going to be a hole in the graph. Now, if you graph this on your graphing calculator, because this is just like a infinitesimally small, it's just like a little pixel, you're not going to see the hole. But if you go to your table, you'll see that there's an error at negative 3. Like it can't be negative 3 because we can't divide by 0. Now, even before you cancel these factors out like this, you might want to analyze the domain. We said you can't divide by 0, that's undefined. So you can see that the domain is going to be all real numbers, but x cannot be negative 3, and it cannot be 4, because that would make the denominator 0, right? So you could also write it like this, from low to high, negative infinity to negative 3, and then from negative 3 to 4, and then from 4 on to positive infinity. Okay, now if we talk about the vertical asymptotes, we said we can't divide by 0, right? So what would make this denominator 0? It would be x equals 4, because 4 minus 4 is 0. And so we're going to have a vertical asymptote right here at 4. Right here at 4. So now you might be saying, well, what about here, negative 3? That would make the denominator 0, but that's where our hole was located. So it's either going to be a hole or a vertical asymptote, but not both. So now let's look at the horizontal asymptote or the slant asymptote. Here's where we focus in on the highest powered term in the numerator, the highest powered term in the denominator. Now, if it's a tie, like see how these are both x squared, then what we do is we take the ratio of the coefficients in front of those variables. So in this case, this is understood to be a 1 and a 1. So 1 divided by 1 is 1, and our horizontal asymptote is going to be right here at y equals 1. Now you might be saying, Mario, why is that? Well, what happens is x gets bigger and bigger. Like say if we put x as 100 in, way over here to the right. This term is going to go faster than this term. This term is just going to stay at negative 12. So as this gets bigger and bigger, this term is going to be much more influential. These are going to not really have much of an effect as x gets really big. Same thing with the negative 9. So this really reduces or acts like x squared over x squared. Anything divided by itself, that's going to cancel out, and you're left with 1 over 1, which is the ratio of the coefficients. The last example, remember how the denominator's degree was higher? That's y equals 0. It's going to get closer to 0, which is the x-axis. And we're going to do some examples where the numerator's power is greater by a power of 1, and that's where we're going to get the slant asymptote. So that's coming in the next examples. So now for the y-intercept, what we do is we set x equal to 0. So if I put 0 in for x, that's going to be negative 3 over negative 4, which is 3/4. So that's going to be right about here. Now you might be saying, why didn't I use this one? I could use this one too. If I put 0 in for x, all these are going to cancel out. Negative 9 over negative 12 is also 3/4. It's just that the graph's basically going to look like this with the added feature of having that hole there. Now with the x-intercept, we set the y coordinate to 0. And again, remember the shortcut is the only way that y is going to be equal to 0 is if the numerator's factors are equal to 0. So if I set x minus 3 equal to 0, I'm going to get x equals 3, which on my graph is going to be right here. Now you might be saying, oh, I don't like that method, Mario. So you could say, well, okay, y is equal to 0, which is like 0 over 1. Remember our graph is going to look like this reduced function, x minus 3 over x minus 4. You can cross multiply, remember on the diagonals, 0 times anything is 0. X minus 3 times 1 is itself, and if you add 3, you can see you're getting x equals 3. Some students like this much better. Now we need to plot some additional points, but remember, we can't go through this vertical asymptote. It's like a brick wall. Graph either has to go up towards positive infinity, down towards negative infinity, right? How do we know what's happening? Let's pick some points on either side. Let's pick 3.5 and like 4.5, or maybe even 5. So let's do 3.5 first. So I plug in 3.5, I'm going to get a positive in the numerator. This is the sign analysis. 3.5 minus 4, I get a negative in the denominator. A positive divided by negative is a negative, which kind of makes sense. This is going down, down, down. So you can kind of see this graph's going to look like this. Okay, and you got that branch. Now if we do 5, that's going to give us a positive 2 over a positive 1. Positive divided by positive is a positive, which tells us from this direction we're going to be going up towards positive infinity, and then we're going to approach that horizontal asymptote as we go to the right. And you've got a good sketch. Let's take a look at another example. Okay, let's take a look at example number 3 now. We've got this polynomial divided by a polynomial, a rational function. First thing we want to do is factor, right? So in the numerator, it looks like we can factor out an x as a greatest common factor. And if we do that, we're going to be left with, let's see, 2x squared plus 3x minus 2. The denominator we can factor. It's going to factor to x minus 3 and x plus 1. This trinomial we can factor a little bit further. So that's going to factor as, let's see, 2x and 1x. And let's see, this is going to be plus 2 and minus 1. And then we have our denominator x minus 3x plus 1. Okay, so basically our equation is going to look like this guy right here. Let's circle that. Okay, in factored form. So the first thing we want to analyze is, are there any factors in the numerator that cancel with factors in the denominator? If there are, we know there's going to be some holes in our graph. In this case, there's no factors in the numerator that cancel with factors in the denominator, so we're going to say that there's no holes or none. Okay, now for the vertical asymptotes, we know we can't divide by 0. So if we set these factors equal to 0 in the denominator, x minus 3 equals 0, x plus 1 equals 0, we're going to get x equals 3 and x equals negative 1. So let's go ahead and plot that on our graph here. So negative 1, try to be real accurate about this. So here's negative 1, and x equals 3 is going to be right here. Just trying to draw it as a dashed or dotted line. You won't actually see that on the graph. It's just kind of using it as a guide. Now the next thing we want to do is we want to analyze, do we have a horizontal asymptote or a slant asymptote? Well, in this problem, you see how the highest degree term in the numerator is higher than the denominator's highest degree by 1. So what that tells us is we're going to have a slant asymptote, like a diagonal or an oblique asymptote. How do we find the equation of that oblique asymptote or slant asymptote? We're going to do long division. So I'm going to take the numerator divided by the denominator. So we're saying how many times does x squared minus 2x minus 3 go into 2x cubed plus 3x squared minus 2x plus 0. Okay, so you probably learned this before, polynomial long division. How many times does x squared go into 2x cubed? That's going to be 2x times. I'm going to distribute the 2x to all three of these terms. That's going to give us 2x cubed minus 4x squared minus 6x. You can subtract, or what some students like to do is change the signs to the opposite and add. So that's going to give us 7x squared plus 4x plus 0. How many times does x squared go into 7x squared? That's 7 times. If I distribute the 7 to all three of these terms, I get 7x squared minus 14x minus 21. If I subtract or change the signs to the opposite and add, that's giving us 18x plus 21. And when this degree, x to the first, is lower than this degree, x squared, that's our remainder. We don't have to worry about the remainder. So our equation of our slant asymptote is going to be y equals 2x plus 7. So that means it has a y-intercept of 7, 1, 2, 3, 4, 5, 6, 7, right about here, a slope of 2, which means I'm going to go rise 2, run 1, like this. So down 2 over 1, cross right about here. Let's repeat that, down 2 over 1 right about here, down 2 over 1 right about here. Let's see, down 2 over 1 right about here. So roughly, let's repeat this a little bit here, up 2 over 1 and up 2 over 1 up to, okay, so basically like this. I'm trying to be accurate. We don't have graph paper here. I don't have graph paper on this screen here on this board, so we can just kind of estimate like that. Okay, so now let's focus on the y-intercept and the x-intercept. So to find the y-intercept, we set x equal to 0. And if we put x equal to 0, you can see that this is going to be 0 over -3, which is just 0. So that tells us it's going to go right through the origin here. Let's put a point right there. And the x-intercept, we're going to set y equal to 0. Now remember, when y is equal to 0, the only way that y is going to be equal to 0 is if the numerator's factors are equal to 0. So that's going to occur at 0, 1/2, and -2. So let's see, let's plot that. So 0, 1/2, which is right about here, and -2, which is right about here. Okay, so that's interesting. And now some additional points. Now we want to plot some points on either side of the vertical asymptotes. So let's maybe start over here. Let's do -1.5. So if we plug in -1.5, we're going to do our sign analysis. We're going to get a negative. This is going to be a negative. This is going to be a positive. And then we've got a negative and a negative. Okay, so we get a positive divided by positive, which is a positive. So what that tells us is that this graph is actually going to go up towards positive infinity right here when we're just to the left of this vertical asymptote. So what's happening here, I don't know if you can see this, is this graph is basically going like this. Okay, so as you go here, it's approaching the slant asymptote, but as it approaches this way, it's going up towards this vertical asymptote, so something like that. Now let's approach this vertical asymptote from this side. Let's say we put in a -1/2, okay, -0.5. So what happens when we do that? We get a negative, this would be a negative, this would be a positive again, this would be a negative, and this would be a positive. So we're getting a positive over a negative, which is a negative. So that means from this side, it's going down towards negative infinity. Now, if we approach this vertical asymptote, let's see, 1, 2, maybe like 2.5, what are we getting? We're getting a positive. We're getting a positive. You can get the exact number if you want. This is just a little quicker way of doing it, and a little bit more fun too, I think. So this comes out to a negative, and this comes out to a positive. So we've got, let's see, a positive divided by a negative, which is a negative. So that tells us on this side we're going down like this. So here you can see that this graph's going something like this. It crosses a little bit the x-axis, and it approaches these two asymptotes. Now if we approach from this side, let's see, 1, 2, 3, let's maybe put 4 in. Let's see what happens when we plug 4 in. We get a positive, we get a positive, we get another positive, okay, and then over here we get a positive and a positive. So you can see everything is positive. Positive divided by positive is a positive. That tells us from this side we're going to be going up towards positive infinity, and this branch is going to go approach that slant asymptote. Now here's the questions that people are probably thinking. They're saying, Mario, how did you know it bends right here? Like how come it doesn't go all the way down to right here and then go like that? Or how come it doesn't bend over here? This is what you learn when you get to calculus. You're going to learn how to find where the tangent line, the slope of the tangent line is 0, and you're going to be able to find exactly where that minimum is or exactly where this maximum is. But for this video, we're just going to talk about getting a really good sketch without being super precise about some of these extremas are called, these bends or maxes or mins. So good job on this one. This one was a slant asymptote, remember, because the degree in the numerator was 1 higher than the highest power term in the denominator. Let's take a look at 2 more examples. Okay, before we dive into these last 2 examples, if you like the way that I explain things and you want to go deeper with your math learning with me, check out my Algebra 1 and my Algebra 2 / College Algebra video courses for sale. I take you step by step through a typical Algebra 1 or College Algebra curriculum, and I'll put links in the description below. Also, if you just want to support the videos that I'm putting up here on my Mario's Math Tutoring YouTube channel, consider joining as a channel member. So for a few dollars a month, you can support the videos that I'm putting up here, and I really appreciate that. I see every member that comes through with the channel name or the name of your your YouTube handle, and I can see that you're a member of the channel, and I really appreciate that. And then lastly, if you just want to purchase one of my fun math t-shirts, you'll see below the video I've got some links to my Teespring store, so you can purchase one of those t-shirts if you want to just kind of have some fun with my channel here. So let's dive into number 4 and number 5. So for number 4, we've got f of x is equal to 3 over x squared plus 1. So what's our first step? First step is always to factor as much as you can, but in this case, we cannot actually factor this. So, okay, we don't have to worry about that. So now what about the wholes? Are there any factors that cancel with the numerator and the denominator? Well, in this case, no. So we're going to say no wholes here. How about vertical asymptotes? Vertical asymptotes is when we set the denominator equal to 0. If we set the denominator equal to 0, let's just do that for a moment. Subtract 1 from both sides, take the square root. The square root of a negative number, you get imaginary numbers. So that tells you that there's actually no vertical asymptotes on this graph. So this is kind of a little bit different than the first 3. Now for letter C, horizontal asymptote or a slant asymptote. Here's where we analyze the highest powered term in the numerator and the highest powered term in the denominator. So in this case, you can see because the degree of the highest term in the denominator is higher than the numerator, the horizontal asymptote is going to be y equals 0, which is right here on the x-axis. And again, you can think about this as x gets really large. Like say, for example, if x was like 100. 100 squared is 10,000, plus 1 is 10,001. What's 3 divided by 10,001? It's like 0.00, it's approaching 0 basically, right? So now for letter D, the y-intercept. So to find the y-intercept, we set x equal to 0. And if we do that, we're going to get 3 over 1, which is 3. So that means that this graph is going to cross right here at 0, 3. The x-intercept, we set the y-coordinate to 0. So if we set y equal to 0, that's like 0 over 1. And if we cross multiply here, we get 3 times 1 is 3 is equal to 0, which doesn't make sense. 3 can't equal 0. So that tells us that there's really no x-intercepts. Okay, so it's not crossing the x-axis. And then let's plot some additional points. Now normally I'll pick some points on either side of the vertical asymptote, but there's not a vertical asymptote. So let's just pick some points on, on either side of this y-axis. Let's just do, let's say for example, -3 and +3. So if I put in -3, I get -3 squared is 9, plus 1 is 10, 3 over 10. And if I plug in +3, I also get 3/10. So that's interesting. So -3, 3/10 is right about here, and +3, 3/10 is right about here. I can plot some additional points as well. Like maybe let's plot -1 and 1. That would give us 1.5 and 1.5. So that's going to be right about here and right about here. So you can see this graph is basically, it's going like this, where it's approaching the x-axis as you go to the left, it's approaching the x-axis as you go to the right, and it's like a symmetric. If you fold over the y-axis, it's going to match to itself. So this is a little bit different graph. Let's take a look at one last example. Okay, let's dive into example number 5, and if you want more practice with these problems, I'll put a link at this end of this video. I'll indicate where you can click to see some other video that I did previously talking about how to graph these rational functions. But for number 5, how do we graph this one? Well, this one we notice that we need to factor it first as much as we can. So I notice I can factor out an x as a greatest common factor in the numerator. And the denominator looks like we can factor into 2 binomials. What multiplies to 2 but adds to -3, that's going to be -2 and -1. And it looks like I can factor this numerator a little bit further, x plus 3, x minus 2 over x minus 1, x minus 2. I notice I just flipped these. And so notice here that there's a factor in the numerator that cancels with the factor in the denominator. So that tells us that there's going to be a hole in our graph, right? And that x according to the hole, if we set this equal to 0, x minus 2 equals 0, x is equal to 2. So we're going to have a hole at when the x is equal to 2. Now, how do we find the y coordinate? We take that 2 and we plug it back in. So that's going to be, let's see, 2 times 5 is 10 over 2 minus 1, which is 1. So that comes out to 10 over 1, which is 10. So let's see on our graph here, 2, 10, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right about here, okay, is our hole. Now for the vertical asymptotes, we want to set the denominator equal to 0, because we can't divide by 0, that's undefined. So if I set this equal to 0, that means that x equals 1 would be our vertical asymptote. So that's going to be right here. Draw this as a dashed or dotted line right through x equals 1. And then for our horizontal or slant asymptote, which one do you think it is? Well, notice that the degree in the numerator is 1 higher than the highest power term in the denominator. That tells us we're going to have a slant or a diagonal asymptote. And the way that you find the equation of that asymptote is to do some long division. So we're going to figure out how many times does x squared minus 3x plus 2 go into the numerator x cubed plus x squared minus 6x plus 0. So x squared goes into x cubed x times. If I'm going to distribute the x to all three of these terms, that's going to give us x cubed minus 3x squared plus 2x. Subtract, or you can change the signs to the opposite and add. So that gives us 4x squared minus 8x plus 0. How many times does x squared go into 4x squared? That's 4 times. If I distribute the 4 to all these terms, I get this. And if I subtract, which is like changing the signs to the opposite and adding, we get 4x minus 8. And notice that this is x to the first, this is x squared. Normally what we do is we put our remainder over our divisor, right, when we do our long division. But what happens is see, as x gets larger and larger, this whole fraction is going to go to 0 because the degree in the numerator is higher than the degree in the denominator is higher than the degree in the numerator. So this whole thing goes to 0. That's why I say we don't have to worry about the remainder. Our slant asymptote is just going to be the line y equals x plus 4. So let's see if we can graph that on our graph. We have a y-intercept of 4 and a slope of 1. So it's going to go like this. Try to be accurate here as much as I can. Something like this. Okay, there's our slant asymptote. Now, let's analyze our y-intercept and our x-intercept. So what I like to do is make a table, and you set the opposite variable to 0. So if I want the y-intercept, I put 0 in for x. If I put 0 in for x, you can see I'm going to get 0 over 2, which is 0. So that means it's going to go right through our origin here at 0, 0. If I want to find the x-intercept, I set the y equal to 0. Now the only way that y is going to equal 0 here is if the numerator's factors are 0. So that would occur at 0 and negative 3. So that means it's going to cross at 0 and negative 3. Okay, right here. And then let's plot some additional points. Now the key points are the points on either side of the vertical asymptote. Because remember, it's like a brick wall. It either has to go down to negative infinity, up through positive infinity. Can't go through the brick wall, right? So let's maybe plot a half. So if we put a half in, what happens? We get positive, positive, which is going to give us a positive when you multiply, over a negative. A positive divided by negative is a negative. So that tells us it's going to go down like this. So we can see what's happening here. The graph's going like this and like this, approaching that slant asymptote, getting closer and closer. Now if we pick a point on this side, let's say for example like 2, that's going to give us a positive, positive, which is a positive, over 2 minus 1, which is positive 1, that's a positive. A positive divided by a positive is a positive. So from this side, it tells us this graph's going to go up towards positive infinity. Now this graph's going to go something like this. Okay, now again, we talked about this in a previous example. We don't know exactly where this graph is bending without using calculus. We have to find out where the slope of the tangent line is equal to 0 to find these extrema, these maximums and minimums. But for this video, for this, what we're doing here, we're just getting a basic sketch. We've got our intercepts, we've got our asymptotes, we've got our holes, we've got some, sign analysis to tell us if the graph's going up to the right or down to the right, up, with the asymptotes where it's approaching, etc. So great job. I hope you picked up some good pointers in this lesson, but if you want more practice, follow me over to that video right there where we dive into some more examples graphing rational functions. I'll see you in that video.